Hi everybody, welcome to another video in statistics, section 6.2, binomial probability distribution. Binomial probability experiment. So, definition, in a binomial experiment, these four things have to happen. The experiment is performed a fixed number of times. So, for the fixed number of time, or we call trial, fixed number of trial. Like if we flip the coin 10 times, we know exactly that it will be 10 times, not more, not less. The trials are independent. So if we toss in the coin 10 times, each time the probability of getting a head or a tail will be the same every single time. Right? Unless you throw the coin very hard and you bend it and the probability will change. But on that extreme circumstances, we're not worried about those things. For each trial, there are two mutually exclusive or disjoint outcomes, success or failure. So we have either like a coin, head or tail. We don't have anything other than those two. Only two mutually exclusive outcomes. And the probability of success is fixed for each trial of experiment. So we know exactly the probability of getting each particular case for each outcome, for each trial. Right. The notation we call N is the number of trial. P denote the probability of success. Success here is defined as whatever the design outcome we want. And let capital X be the random variable and little x is the number of success. So the number of success is defined by the little x. So there are three variables. N is the number of trial, and that have to be fixed. P is the probability of success, and that also fixed. And X, number of success, and that is what we want in each case. Right here, an example. Which of the following are binomial experiments? A player roll a pair of fair dice 10 times. So we have the number fixed. N is equal to 10, so that's good. We have that. Next is the fair dice. So when we're rolling, the probability would be the same every single time. So P is fixed. I should say it's independent. That more. And X is 7 roll. So we know the fixed outcome of each time is getting the sum of being 7. So either getting 7 or not 7, right? So X number of 7 room. So either we get a 7 or not 7. So we have two clearly mutually exclusive outcomes. So that check as well. And so this is the success here is getting 7. Not getting 7 is it's not success. And the number of X. So in that case, this is a binomial experiment because we have everything. Right? Fixed number of trial, probability are independent, and we have the outcomes, two outcomes. Right, next, the 11 largest airline had an on-time percentage of 84.7 according to some data. In order to assess reasons for delays, an official with FAA randomly select flight until C510. Right, so this is not binomial because he select until C510, so there's no fixed number of trial. So N is not fixed. So we don't have the fixed number of trial. So that is not binomial. By the way, bi means 2. So there's only success or failure. And like I said, success or failure is the way we define it. Right. In a class of 30 students, let's say the 60 instead of 55, because 55 is not 55% of 30 is not even, it's not a whole number. So let's say 60, right? That's fine. The instructor randomly select 4 students. The number of X of female select is recorded. Right. Now here's the problem. 30 students, 60% are female. So 60% of 30 is 18. So 18 female and 12 male. The probability of getting a female is 60%. That's true, but that only for the first person. After the first person, the second person heavily depend on that. So if the first one is female, we have 15 out of 29 left. If the first one is male, we have, the 18 female, right? So if the first one is female, we have 17 out of 29 of getting female, the second one. If the first one is male, then we still have 18 out of 28. So that is not independent. So we say, is this the trial are not independent because the probability will change from trial to trial. So that, once again, is not binomial. The first one is a binomial experiment. Right, an exam has 25 multiple choice questions. Yes, so we have the number of fixed trial. If a student answers the question at random, so multiple choice question where there are 3, let's assume that the same type of multiple choice question where there's 4 options. Alright, let's assume that. If a test if the question have 3, a question have 4 or 5, it will not be binomial. Assume that every question has 4 choices and one of them is correct. So the chance to answer the question correctly is 1 out of 4. So if we say answer the question correctly is success, then that probability of success is 1 out of 4. Now, of course, we can also consider success to be missed answer the question that she missed. So the probability that she missed, let's say 4 choice each question. So the probability that she will miss is 0.75 or 3 out of 4. And if the student answers at random, whatever the first question is doesn't depend on the second and so on. So in that case, it is independent. So trials are independent. Trials are independent, and the probability of success is, in this case, success is miss the question, 75%. A probability of failure is complement to that is 25%. So yes, this one is binomial because we have fixed number of trial. The trial independent. There's success and failure. I mean, get the question correct or not, and there are 2 outcomes, and those are, two outcomes, and the probability to get each one are the same for everything. So yeah, so that is binomial. Right, now let's look at the problem without any formula. We just do that the intuitive way. Right, now a fixed coin is tossed 4 times. Now this is not a fair coin, so that we have the head at 60% and tail at 40%. Let X be the number of heads observed. Compute the probability distribution. Now first, I will list all the outcomes here. Right. So now, just like the chance on the right hand side, I will alternate every one. So just head, tail, head, tail, head, tail, and so on. A second one, alternate every 2, head, head, tail, tail, and so on. next one will alternate every 4, sorry. So 1 times 2 times 2 is 4 times 2 is 8. Head, 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 head. Tail, 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 tail. Head, 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 head. Tail, 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 tail. And the first one will be A heads. And A tail. Right. Now the probability, once again, probability of getting a head is 60%, a tail is 40%. So in this case there are 4 heads. So if I just write 0.6 times 0.6 times 0.6, or 0.6 to the 4th power. Right, next 0.6 for a head and 0.4 for a tail. So I have 0.6 times to the 4th power times 0.4. Right, I'm not going to multiply to write everything here, just write everything with power. So here we have 3 heads and 1 tail. So 3 heads and 1 tail. 2 head, 2 tail. Sorry. Yeah, 3 heads and 1 tail. So this should be 3. And here 3 head. So 0.6 3 times 0.4. 2 head, 2 tail. 6, 2, 0.4, 2. 2 head, 2 tail again. 2. And a head. And 3 tail. 3 head, 1 tail. 2 head, 2 tail. 2 head, 2 tail. And then 2 tail and 2 heads. 1 head, 3 tail. 1 head, 3 tail. And 4 tail. Right. So it's easy, right? Just multiply probability for each one, and that's what we have. Now let's count. How many we have? 0 heads. This is 0 head. Only this last case. And how many do we have? Just that. Just one case. Now how many we have? That is, let x be the number of heads. So how about how many of these we have 1 head? So 1. That we have 1 head. 1 head here. One head here. There are 4 of them. And each one of them, of course, we see 0.6 and 0.4 cube. So 0.6, and this to the 3, so this to the first power. Yeah. So, and yes, so pretty much we have the probability of getting 1 hat is 0.6 times 0.4 cube, and we have 1, 2, 3, 4. We add all of them up, that means we have 4 of them. Let's count again. 1, 2. I miss. Next, how many we have 2 hats? This we have 2 hats. 2 hats. 3, 4, 5, and 6. So 2 hats, probability is 0.6 square because we have 2 hats, and that's got 2 tails. And how many we have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So there are 6 of them. And now 3 hats. 1, 2, 3, 4. 4 times, and to get 3 hats, 0.6 cube, 0.4. And finally, there's only one case, there's 4 hats. And there's only one chance here. So, that's what we have. Of course, from here we can find the numbers, but that's not really important. Right? So, that's what we have. Of course, we come up with the formula in a little bit, but right now just intuition. That's what we come up with. Now forget about the probability of getting hat or tail on that coin. Find out how many outcomes for getting X hats. Right. So therefore, 4 trial. And out of this, how many hats we can have? Let's say if we have 0 hat, there must be only one outcome. Tail, 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 tail. Now, for 1 hat, how many outcomes do we have? Think about that. So meaning there's a 4. One of them have to be a hat, right? So just like this is the combination. Pick 1 out of 4. So we choose one of them to be hat. The rest will be tail. So we have a combination of 1 out of 4 outcomes, and we can list them, but there will be 4 outcomes. Of course, yeah, because we're going to pick 1 out of 4, so that's 4. Now if we have 2 hats, we're going to pick 2 hats out of 4. Pick 2 out of 4 to be hat, and so that will give us 6 outcomes. Pick 2 out of 4, there's 6 outcomes. And 3 hats will be 4. Pick 3 out of 4 to be hat, and that will be 4 outcomes. And if we have all hats, so we have to pick all 4 of them to be hats, and that will be 1 outcome only. And that particular, of course, hat. And 0 hat will be 1 outcome, so we can also write this as C picked in none R4. Right. So with that, we can come up with the probability of getting X hat will be equal to how many X hat that we want R4, and when we have X success, 0.6 getting a head and 0.4 when getting a tail. And if we choose X of them to be head, 4 minus X will be tails. Right? The number of total outcome, the number of trial is 4. So X of them is head, 4 minus X of them will be tail. So that is the formula in general. I copy a type the wrong formula here. This should be n minus x, where x is anything from 0 to n, where p is the probability of success. Now put all of that together, we're going to select 0 out of 4, and probability of getting hat is 0.6. Here we have 0 hat and 4 tails. Right, so we do that. Next, we're going to pick one of them to be head, and 3 of them will be tail. So 4 minus 1 is 3. And then next, we're going to pick 2 of them to be head, and 2 heads, so there will be 2 tails. Now we pick 3 of them to be head, and so 1 of them to be tail. And finally, we pick all of them to be head, and there's no tail. Yeah, just do the math and get the answer. Alright, so for math, probability combination, I should choose, once again, for math, probability, just pick 0 first, and then we have 0.6 to the 0 power, and 0.4 to the 4 power. Right, so we have that. Should we look at this? There's only one probability that have head. So we have that. Next, no, this is not equally likely outcome, so we don't just count. Right, next. So I need, wait, did I try that look differently? Let's do this again. For math combination, select 0 out of it, then we have 0.6 raised to the 0 power, and 0.4 raised to the 4 power. Right, we have that. Now, if we're going to pick, there's one head, so this will be to the first, and this will be cube. So that's 0.1536. And now just copy and paste, turn this to 2, 0.3456. That to 3, 0.3456. And now select all 4 of them to be heads. .1296. Just to be safe, add all of this up to see if we have 1, and we should have 1, right? 0.0256 plus 0.1536 plus 0.3456. And we do have 1, so it's good. Alright, so the formula is that how many number of trial, so we toss the coin 4 times and we count how many head we have, and each time we have a head, that's 60%, each time we have a tail, that's 40%, so that's what we have. Of course we can use the calculator to calculate this as well. Now before that, let's go over some technical terms. When we have a certain situation here, I suppose the probability that damaging hail occurs in a year at a certain city is 3%. Find the probability that in 10 years there are exactly 2 years with damaging hail. Alright, so we just have, in this case, 10 years. So that fixed number of trial, n equal to 10. Exactly 2 years, so that would be x equal to 2. And the probability that have the damaging hail is 3%. Right. Yeah, so pretty much that. So now we have the probability of getting exactly 2. Right, so that means if we use a formula, there are 10 years, we're going to pick 2 of them to have damaging hail, right? And when we have damaging hail, the probability of that is 0.03, and there are 2 of them that have damaging hail. The complement of that is not getting hail in the order 8 years, right? Of course, the formula is that. But like I said, if we know about each component, it will be better. So we choose 2 of them out of 10 to have damaging hail, so it's 10C2. And then each time we have the damaging hail 0.03 to the second power, there are 2 damaging hail year. And then not the complement to that, there are 8 years left that doesn't have hail. Right, so just put all of that in the calculator. 10 math 1 big 2, and then times 0.03 raised to the second power, and then times I already do the math, but I should say 1 minus 0.03, the complement to that, which is 0.97 raised to the power of 8, and we have 0.0317, so this is 3.17%. Right, so straightforward. How many we have, how many we need in the total number of trial, and each time of success we have the probability with the corresponding power, the number of success that we want, and then the complement to that is the probability of failure and how many times we have. Alright, so the formula is kind of straightforward, but when we do the math, it's a little bit tricky when we have the wording in it. So first we say at least no less than or greater than or equal to. That's what the symbol means. Greater than or equal to. More than or greater than equal. More than, no equal. Fewer than, no equal. No more than, at most, less than or equal to. So all of that is that simple. And exactly equal is meaning equal. Right, so sounds straightforward, right? Right, let's see. According to Experian Automotive, 35% of all car owning households have 3 or more cars, right? So we have the probability of something that is 35%. 5 in a random of 20 car owning household. So we have fixed number of trial 20. What is the probability that exact 5? Yeah, so we have that. So now if we want to use stick with the formula which is 5, so we say binomial and px in alphabetical order is combination of pick an x out of n, p to the x, and 1 minus p to the n minus x. So straightforward. So there are 20 households and we want 5 of them to have 3 of 4 cars. Next, the probability for that will happen is 0.35 to the 5, and then 1 minus 0.35 to the 20 minus 5. Right? Of course we can do that, but it's better yet. Let's do that by hand first. So we're going to pick from 20. Keep doing that. Pick 5 out of those, and we have 0.35 to the power of 5, and then times 1 minus 0.35 is 0.65 to the power of 20 minus 5 is 15. So we have 0.1272 or 12.72%. Now there's another way to do this. Is second distribution go to the first one, normal PDF, and the x values, second distribution, and we have to go to binomial, which is way down here. Choose the binomial PDF, not the CDF, the PDF. Right, actually we need to clear everything. Let's do that again. Second distribution, go to option A. Right, number of trial we have 20. Probability of success 35%. And how many we have? Exactly 5. Right. And of course that's what we have. Right. Next, in a random of 20 cars owning household. So once again we have n equal to 20. What is the probability that less than 4? Right. Now less than 4 meaning x can be 0, 1, 2, or 3. Less than 4 have 3 or 4 more cars. So in that case, meaning we have to do all 4 of them and add together. So I'm just going to say it's going to be binomial one of them, there's 20 household and none of them have more than 3 cars. I mean the probability is 35%, and then exactly none of them have 3 or 4 cars. So we do that for an x equal to 0, and now we do the same thing. And we have 1 household, and then 3, 2, and then 3. So add all of them up. So again, second variable. Right, so we're going to have 20, the same thing, but this time we have 0. Right, save that. Now we do this again, but this time there's 1. Now we do this again. This time we're going to choose 2. And do this one more time. This time there's 3. Right. And then we just add all of those numbers up. Here's 1. 2. 3. So when we just go highlight and then hit enter, that copy and paste, add all of them up, we have all together is 0.0444, right, 4. Right. Now there's another way to do this. If we get x from 0 to 3, so we do is it's going to be normal CDF. I just keep doing that. It's binomial CDF. The C stands for cumulative. Right? So, sorry. Second variable. And then we go to binomial CDF if we want more than one values. Right? There are 20 trials. 0.35 probability of success X. I'm just going to put 3. So this normal CDF meaning it cumulatively calculate from 0 up to that number. So if we want from 0 to 3, that's what we put. You see? Right, next. In a random of 20 car owning household, so once again n equal to 20, and at least 4, meaning x is greater than equal to 4. So of course we can do that for 4, 5, 6, 7 all the way to 20, but that will be too much. What we see here is 0, 1, 2, 3 and greater than equal to 4. Those are complement of each other. So we'll say probability of getting x greater than or equal to 4 is complement. So it's 1 minus probability of getting the number less than 4. Probability of less than 4 here will be exactly as we have on the previous pocket problem. So 0.04435756. So just do that. Or we take 1 minus this. And we have 0.9556. Right. So it's easy to find a binomial PDF for one values, CDF for all the values from 0 to that number. So have to be mindful with all the wording here because that's very important. Okay. So here's some the note that we need to use on the calculator. The syntax is binomial PDF. We calculate exactly getting x successes. The CDF cumulatively from 0 to x. PDF for one values, CDF for everything from 0 to that particular values. Now, in a recent survey, 60% of the community favor building a health center in their neighborhood. 14 citizens are chosen. Find the probability that exactly 8 of them favor the health center. So when we look at this, 14 citizens are chosen, so we know n is equal to 14. 60% in favor, so p is 60%. And exactly 8, so x is equal to 8, exactly. So we go to binomial PDF, and we put 14.06 for probability and 8. That's what we have. Right? Of course, the key sequence is going to be that. Right. By the way, how do we use the StatCrunch. Just go there. So we go to StatCrunch. We go to stat, and calculators, binomial. Right, so in this case, let's say we have 14, and the probability of success 0.6, and we have exactly 8. And then compute. So we get the same thing. 0.2065 something. Let me go back to, yes, the note, which is exactly that. I should start run once again. I'll close this. Just go to stat, calculators, and binomial. Enter the numbers, right? N, P, and X. We can choose less than, greater than, equal to. The StatCrunch have a lot more advantage than the TI calculator here. Right. For that next problem. A quiz consists of 10 multiple choice questions, each with 5 possible answers. So we have fixed number of trial, 10 trial, and each with 5. So to get correct answer, we have to choose, there's only 1 out of 5, or 0.2. Sorry, I didn't have the note there. Right, once again, the quiz consists of 10 multiple choice questions, so n is equal to 10, each with 5 possible answers. So one of them is correct out of 5, so 1 out of 5, 0.2. Now, to pass the quiz, a student must get 60% or better, right? So to pass, we require the number of success have to be 60% or higher of 10. So there are 10 questions, 60% of 10 is going to be 6. So x have to be greater than or equal to 6. Right. The problem with this, they have multiple values. When in multiple values, we should use binomial CDF. But the CDF only calculate from 0 to a number. This is greater than or equal to 6, so that doesn't work. So let's say if we have 10 trial, the number of outcome, we have 0 question correct, 1 correct, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we want to pass, we have to have 6 or more questions answer correctly. In that case, we have the complement of that is 5. Right? So, if we write probability of getting x greater than or equal to 6, if we use TI calculator, we cannot do greater than. So we have to take 1 minus p of x less than. Yeah, calculator can calculate, the TI calculator can calculate anything less than, cannot calculate greater than. I mean, should be actually less than or equal to. That is less than 6 is equivalent to less than or equal to 5. Right? Less than 6, less than or equal to 5. So we're talking about discrete, so we don't have a 5.5 or 5.9 here. Have to be whole number 6, 5, or so on. Right? So, and we put that in the calculator. That's what we have. Right? Now the StatCrunch. The nice thing about StatCrunch is that we can put less than, greater than, all kind of numbers. So first, there's 10 questions, that's correct, and 1 correct answer out of 5 choices, so that's 0.2, and then x in this case is greater than or equal to 6. So StatCrunch is very easy. We can just enter that exactly and we compute, and that's what we get. Right? Let's say if it's instead of less than equal to, it's less than 6, that's what we get. Or if we don't want 6, we want less than or equal to 5. That's the same thing, right? So less than or equal to 5 is the same as 6. The note here is binomial CDF only from 0 to x. Particularly, this should be only for x for less than equal to whatever that is. If it is greater than, I just keep doing that, sorry, I have to switch to the note. Right. What I'm saying is binomial CDF, it only works for less than equal to whatever that number is. If it is greater than or equal to, we have to write the complement. And if it doesn't have the equal, we have to make it equal so we can use the calculator. Right, so that's what we have. Right. So, on the previous problem, we want greater than or equal to 4. The complement is less than 4. Right? If we don't want to write less than 4, we can also say less than or equal to 3. And that's what we did earlier. So from x equals 0, 1, 2, 3, meaning less than or equal to 3 or less than 4. Either way. Right? Once again, the calculator can only do less than cumulative from 0 to that particular values. So be mindful of the way we enter, what we enter in the calculator. Right? So if we want greater than or equal to 6, we have to do the complement of that, which is less than 6, which is less than or equal to 5. Where we put it in the calculator. Yeah, the CDF. And then 5, meaning it will go from 0, 1, 2, 3, 4, 5. Right. Now, let's say if this is a question, let's say the student don't want to pass. He just want to get at least 5 questions, at most 3 questions correct. In that case, it will be less than or equal to 3, and we can just use this directly. Right? So if we just want for less than or equal to 3, for example, then we don't need to do that. We just say binomial PDF of that, and then 3. If it's less than or equal to, we just use the number. If it's greater than or equal to, we have to use the complement and then determine if there's an equal sign or not. Right. The remaining of the section is we talk about the mean, which is the expected values, and the standard deviation. So the formula will be very simple: the mean and the standard deviation. Look at the example. According to experience automotive, 35%, so we have that. In the sample random, we have 400 car owning household, so n is equal to 400. Probability is still 0.35. Determine the mean and standard deviation. So the mean is NP. So there are 400 households and 35% of them have 3 or more cars. So we just multiply them. Straightforward. It's 140. So the mean is 140. So expected values. So if you select 400 household, probably we get around 140 household that owning 3 or more cars. Standard deviation, square root of n p 1 minus p. So square root of 400 is n times p times 1 minus 0.35. So that's about 9.539. Later on, this might have some meaning, but as far as statistical, the expected values has a lot more meaning than the standard deviation in this case, in binomial experiment. Right. Next, we just have some different case, and we plot, do the histogram for the probability distribution. And we say that when we have, in this case, it's roughly bell curve. So we have some properties here. For a fixed probability, as the number of trials in the binomial experiment increases, the probability distribution becomes bell shape. So the rule of thumb is when this greater than equal to 10, that is bell shape. And if it is a bell shape, then empirical rules say that 95% within 2 standard deviation, and anything outside of that is unusual. So usual or unusual, the break convention is the break off is about 5%. If we have less than 5% chance to happen, that is unlikely. I should say unusual. So unusual is anything less than 5%. Alright, so that's final note. We finish chapter 6. Thank you for watching and see you in another video in statistics.